get going, so keep focus. We'll be able to complete this class much earlier than expected because we only reached 30 minutes. Alright, and amides, we'll do amides and benzene in our next class. And then after that, we just have 1 hour to look at acid and base characteristics of organic compounds. And then module 1 will almost be done because we only have macromolecules to do. And that's something that you looked at in biology. I mean, biology don't teach it properly, so I'm gonna have to do it. Alright, so biology can really handle the chemistry of these compounds, you know, so we're gonna look at it more in depth than what biology looked at it with. Okay, so let's have a look at this now. Esters. So we're going to be naming esters and writing their structural formulae. We're going to be able to describe chemical reactions of esters. We're going to be describing the formation of esters from alcohols. We're going to describe the acid and base catalyzed hydrolysis of esters. Then we describe saponification, then transesterification in its relation to biodiesel. All right. Does anybody remember what saponification is?
Is that when you create the soap?
Creation of soaps. Did anybody create soaps before in fifth form?
Sarah didn't do it in fifth form. I actually did it this year.
This year, okay. Saponification is interesting. All right. So let's have a look at this now. Esterification, right? So it's looking at some esters, right? So esters have a general group COOC, right? So an alkyl group is usually connected to an oxygen, which is also connected to an alkyl group, right? So this is it now. We see the creation of the ester through carboxylic acid and alcohol that we looked at already to create the ester and water, right? It is a condensation reaction of the creation of a smaller molecule here, which is water, all right? Naming them now. Names, we name the alcohol and carb. We name the after, well, it's named after the alcohol and the carboxylic acid, right? So what's happening first is the alcohol name goes first and the acid name goes after. So if we have an ester formed by ethanol and ethanoic acid, it would be ethyl ethanoate. If you have an alcohol created by propanol and butanoic acid, it would be propyl butanoate. All right, so it's just that how it works, right? So we're going to be looking at some of them, right? These are some iconic esters. We have isobutyl formate, which is responsible for the flavor of raspberry. We have butyl acetate, which is responsible for the flavor and smell of apples. Ethyl butyrate, which is responsible for the smell and flavor of pineapples. We have propyl isobutyrate, which is present in rum. It gives rum its flavor, right? And we actually experiment with esters in food chemistry to create different flavors of alcohol. So you have all different types of flavors of rum and all those type of things, right? So if you go into food chemistry, you can experiment with creating all different types of products using different types of alcohols, acids, and esters to create different products. And those products probably make you into a millionaire, right? Because food production is really, really, really lucrative, right? Because imagine you make a new product, everybody likes new product, and then it flies off the shelves. It's going to be huge in the market. So food chemistry is actually a really interesting place of chemistry where you can become a millionaire really, really easy if you just find the right ester. All right. So benzyl acetate is used for peach flavoring. Octyl acetate is what we characterize as the smell of oranges. Right. Wintergreen is methyl salicylate. Methyl phenylacetate is honey, and ethyl methylphenyl glycidate is strawberry. All right, so all of our tastes and characteristic smells, all of them, every single thing is an ester. Don't you forget it. Right, so the sour tastes might be acids, of course, and then the bitter tastes are alkalis. But if you're looking at the smells, characteristic smells and compounds and stuff like that, we're talking about esters. Okay. Hydrolysis of esters. So what is hydrolysis? Hydrolysis is using water to break. So hydro is water, lysis means to cleave, to break, to cut. So hydrolysis is the breakdown of a compound with water. So it's sped up using an alkali or an acid. So we have to look at the acid hydrolysis and the alkali hydrolysis, right? And they are usually hydrolyzed by heating the ester under reflux with the acid or the base. All right. So let's look at this now. Acid hydrolysis of esters. Right? So this is the reverse of the preparation of an ester. So this is reverse, right? So I want you guys to note this. Oh my gosh, why is the pen not writing? Guys, the pen not writing. Okay, the pen is, oh no, never mind, guys. Okay, it's writing. Okay, hold on, the pen is not writing. Okay, so just keep this in mind because my pen is not writing, and that's going to be crazy for mechanisms. I'm gonna have to change the bat. Oh, it's writing now. So it's reverse esterification. Sorry about the writing. So it's reverse esterification. Acid hydrolysis of esters is reverse esterification. Right? So the ester is heated with dilute sulfuric acid and the reaction is reversible, right? So when you do that, you can either create the ester or you can break down the ester. So it's a reversible reaction, right? So the ester is not fully hydrolyzed as well because it is reversible. So the equilibrium position might be to the left, but that doesn't mean that everything is broken down. Remember how chemical equilibrium work, right? So it's not fully hydrolyzed, and we have the carboxylic acid and alcohol being formed, right? So it breaks back down into its constituent acid and its constituent alcohol. Following so far, everybody? Looking at methyl ethanoate and water in the presence of the weak acid, right? Well, the dilute acid. It gives us back the ethanoic acid, right? Or the acetate and the methanol. Any questions?
No, sir.
All right. The basic hydrolysis or the alkaline hydrolysis of esters, right? So in basic catalyzed hydrolysis of esters, the ester is heated with aqueous sodium hydroxide. It is not reversible, so don't think that it is reversible, right? So we need to note that. So it's not reversible. Ester is fully hydrolyzed. Note these changes, guys. Note these, right? An alcohol and a salt of the carboxylate. So the carboxylate is formed, and an ester, right? For an ester like this, the salt of the carboxylate acid arises from the RCO part of the ester, right? And alcohol from the OR part. So this is actually true for both of them, by the way. It's just more descriptive, right? So ethyl acetate with sodium hydroxide will give us sodium acetate and ethanol. You cannot reverse this because you can't just add back water to that to remove this sodium. That don't make no sense, right? So you can't actually reverse this, and they are fully hydrolyzed, right? So they are not reversible reactions. Okay, so note the differences between alkaline hydrolysis and acid hydrolysis. Any issues? Yes, no, maybe, kind of, probably. Nobody? Don't seem like there are any issues. All right. We have a small activity here. I want you guys to try this as well. So you guys got the carboxylic acid one. I want you to try this. So you must give the chemical equation of the acid and alkaline hydrolysis of the following esters and state all necessary conditions. So I want you to give me acid and alkaline hydrolysis for methyl methanoate, methyl propanoate, propyl ethanoate, and ethyl methanoate. Right? So screenshot it or just take it down, note it down. Please try them, and if you have an issue, contact me. Right? So just go into my inbox, put some exclamation mark, shout ambulance or emergency, and I will run come. Right? And I will help you. So basically, if you put it there and ask me a question about the question, you can get an answer. Right? And no, I will not be giving you the answer. Right? I'll help you to find the answer, but I will not give you the answer. Right? So just note that. Okay? So moving on from this slide, if anybody wants to go back, you can let me know. All right. So the key points for this: esters are formed by refluxing alcohols with acids. Right. When esters are hydrolyzed by acids, the products are the carboxylic acid and alcohol. But when they're hydrolyzed by bases or alkaline solutions, the products are a salt, right, a carboxylate, right, and an alcohol. Right. So we don't get back an acid. Okay. So that's what's happening there. All right. So looking at the selected reactions down there, we're looking at the formation of fatty acids, right? Lipogenesis, right? We're looking at saponification and transesterification. So 3 reactions. Okay. If everybody's ready to continue, just drop a 1 in the chat to let me know that we're ready to continue. I want to know if you're ready to continue. I don't know. Don't know if you guys are still digesting information. But yeah, everything should be fine. Let's drop a number 1 in the chat if we want to continue, okay? Sorry for that's fine. Oh, can you go back? Okay, so there it is. That's the activity there. Oh, sorry about that. Just try them. I want you to do the acid and the alkyne hydrolysis of all of them. And please use reversible arrows for acid hydrolysis because you know it's a reversible reaction, right? If you leave off the arrow, I'll leave off your marks, right? If you leave off the state symbols, I'll leave off your grade, right? So don't leave off anything. Chemistry is a really unforgiving science. If you don't practice her, she will forget you and she will move on, right? So you need to practice chemistry. You need to show chemistry some love, okay? So do the practice questions. All right. Well, is everything fine now, Shanique? All right. So let's move on, guys. So fats and oils. So what is the difference between fats and oils, guys? I don't know if you guys remember. Not speaking about esters, no, but what are the difference between fats and oils? Any food and nutrition student here? Because the food students would eat this up immediately,
Fats are solids and oils are liquids.
Love that. All right, so fats are solids and oils are liquids. So the difference between them is the saturation of the double bonds, right? So whether or not they're alkenyl or alkenyl in nature, right? So let's look at this now. So fats and oils are esters of long chains, right? Carboxylic acids with glycerol. So let me fix that error. There's an error right there. I need to move this up to the same line, all right? So fats and oils are esters of long chain carboxylic acids with glycerol. Right, so long chain carboxylic acids are sometimes called fatty acids, as I stated before. Right, the only difference between fats and oils is this solid and oil form at liquid, and the liquid form rather at room temperature. Right, so solid and liquid forms. So the chain length of fatty acids or carboxylic acids in fats are from 12 to 18 carbons long. Right, and fatty acids in fats, right, can be the same or different. So looking at this reaction here, you guys would have done it in unit 1 biology already. So the condensation reaction occurs between glycerol and fatty acids, right? So between the fatty acids and glycerol, right? So the one of the hydrogen from here will be lost, OH from here will be lost, right? And they will actually form the bond along there. And in the reverse, you'll have the hydrolysis, right? Using lipase, right? So from the third form, and you hear about how if you consume fats and oils, there's going to be an enzyme in your duodenum called lipase that break down oils and milk and stuff like that. Yeah, stuff like that. You're gonna have to use lipase to break those down, and that is the catalyst of the hydrolysis of these fats, right? So you guys know enzymes and stuff like that, right? That is what we used to do that. Saponification is the creation of soaps. So all soaps are metal salts of long chain carboxylic acids, right? So soaps are made from boiling fats with sodium or potassium hydroxide. So if we boil, let's say a fat like olive oil, right? And we add in something like citric acid, right? Or we add in something like octyl butanoate or something like that. If we add in a different type of ester, right, into the oil, that's going to give us the smell of the soap, right? Not the flavor of the soap, of course. The smell of the soap specifically, right? And then we add potassium hydroxide if we want liquid soap, and we add sodium hydroxide if we want solid bar soap, right? So there are different types of soap. We have soft soaps and hard soaps, Okay, so sodium hydroxide hydrolyzes the three ester links in the fats, right? So we're looking at the hard soaps, right? The products of sodium salts of the products, sorry, are sodium salts of long chain carboxylic acids, or what we call soaps, right? And the glycerol. So we have the creation of the soap of the fat. So we have the fat here reacting with the sodium hydroxide, as you can see in the reaction beneath there, and we're gonna end up with glycerol and the soap, right? So that is the soap there. What we call a crude soap. What you're gonna have to do after that, you're going to have to pH your soap and you're gonna have to cure your soap before you can actually use it. Because if you don't cure the soap, then it can burn you, right? So it can burn you. And it gives really drastic burns because I've been burnt by it before. Alright, I've been making saponification in the lab without supervision. Sodium hydroxide burned me, then the soap burned me. Alright, so if anybody would understand, it would be me. So the soap actually burns quite, at an intense thing, right? So you need to cure the soap. This is a crude soap, okay? That's saponification, right? Now, looking at chemistry, I'm not sure if anybody see the green engineering syllabus. That's a new syllabus, a new subject at Cape. Under it, it does look at biofuels as well. And I think when we're doing science, we must take into consideration the effects of climate change and multinational corporations and what's happening to the effect of what's happening and how it affects the earth itself. Right. So what we're specifically looking at to understand transesterification is looking at the creation of biofuels, right? So a biofuel or biodiesel in this sense is a fuel for diesel engines that is made with vegetable oils, right? So we can use vegetable oils from plants or we can use fats from animals to create these fuels, right? So these are made by transesterification, right? So first we take the crude vegetable oil through extraction, right? So let's look at it from the fact that in photosynthesis oils are created within plants, right? They're stored in seeds. We're gonna look at how we extract things, right? How we look at oil extraction in module 3, right? Well, module 2 actually. So we're gonna extract the oils from the seeds. We're gonna refine the oil, then we're going to add alcohols to it to make them into esters via transesterification. The glycerol that is left off that goes into food industry or the cosmetic industry, because glycerol is what is in like lipstick and those type of materials, and glycerol is also in food, different types of drinks and highly processed foods. And then what is left off is the biodiesel that we can use in vehicles, and the vehicles would actually produce carbon dioxide that then go back into plants for photosynthesis, etc. All right, so we have that there. So the biodiesel process is important. All right. Transesterification is a reaction of an ester with an alcohol to form a different ester and a different alcohol, right? So we know that trans means different. We looked at trans isomers in geometrical isomerism before, right? And we understand that trans isomers basically means that its functional groups are on different sides, right? But for this, trans means something a little bit different, right? It just means that you're going to take one ester and one alcohol and turn it into another ester and another alcohol. That is what transesterification is. It's nothing more, nothing less. You take an ester and alcohol and you change it into a different ester and a different alcohol, right? So the alkyl group from the alcohol replaces the alkyl group from the ester, which originates from a different alcohol, right? The reaction is slow, so what we're going to do is add heat. So heat is required. Please note your conditions for your reactions, your heat, and you are going to need a catalyst, right? Usually we use alk oxides, right? Like sodium methoxides, right? Sodium methoxides are most common, so use them, right? So for example, we have triglyceride, which we know is a fatty acid and we know it's an ester. All fatty acids are esters. And we react with methanol. What we end up getting is methyl esters and glycerol. So what it does is swap the R groups. Okay? It swaps the R groups. That's all it is. Alright, so that's what's happening. That is transesterification. Any questions? For transesterification? Yes, no, maybe, kinda. I don't know, I kinda know. I don't understand. Is everybody fine? Alright. Seems that everybody's fine. If everything is good, just drop a 1 in the chat, please. And we'll know to move on. If everything is fine, just drop a 1 in the chat and we'll move on. Alright? All right, are those any ones that mean that something is not good? Does anybody have a question to ask? Okay.
Sir, can you go over it again, please?
All right. Okay, so let's actually do transesterification. So my pen does not. Okay, it's working-ish. Okay. So what would mean by transesterification is that we're taking, let's say we have ester A and alcohol A. What we're doing is changing it into ester B and alcohol B. Oh my gosh, this is the ester, this is the alcohol. All right. So what we're doing is changing the ester into a different ester. We're changing the alcohol into a different alcohol. All right. That's what we're doing. That's all what we're doing. Okay, so in this side we have glycerol, right? It's an ester. Sorry, triglyceride. It's an ester, right? So we know that it's an ester because of this group. We see the group. We all see the group. That's an ester group, right? And then we have methanol. We have 3 methanols, right? So let me just draw out the other 2, so you guys can see what's happening. CH3OH. This looks like a 2, right? It looks a little bit messy, but yeah. You just have to bear with me for a second. Right, what it's doing, it's transferring these R groups onto the methanol. We're transferring the R groups. Okay? That's what we're doing. Alright? So when we transfer the R groups, we're going to end up with something that looks like this. We're going to end up with esters that look like this. Alright? So in that case, we have something like that. And then we're going to have the advent of glycerol as the byproduct, right? So what we're doing, we're changing the ester itself. That's what we're doing. Changing the ester. It changes the alcohol as well, but like that's not what we care about specifically. We're just caring about how it changes the esters. Okay? You're not required to know the mechanism for this, by the way. All right, we just have to understand, that transesterification sees the transformation of an ester into a different ester. Right? So we're changing the alkyl groups on the molecule. Following? Following?
Yes, sir. So in simple words, we can just say we are putting the R group on, in this case, the methanol, and we're kind of switching the, what is it called? Basically, the end part of the triglyceride, we're putting it on the OH from the methanol. That's what we're doing.
Basically.
Okay.
Right? So we're transferring the groups, right? We're switching alkyl groups, right? And let's look at a reaction here to understand. So transesterification usually results in a simpler ester. So we have docto. Well, sorry, that's not docto. I'm thinking about inorganic chemistry at the moment. That's like crystal formation. All right, so dodecanyl ethanoate plus methanol. Right? So dodecanyl methanoate plus methanol. Dodecanyl. Dodeca means 12. So 12 carbon today. Alright? So what we have now is methyl ethanoate. But it was dodecanyl. How it becomes methyl? Because we switch the methyl group. So we switch methyl groups, right? So this methyl group replaces this methyl group, in a sense. Or the arrow is drawn a little bit too large. So they replace each other, right? So the methyl and the dodecanyl groups switch. Alright, so they switch places. So we end up with methyl ethanoate and dodecanol. That make more sense? Does that make more sense?
Yes, sir. I can see it better with this.
Okay, lovely. So note that you don't have to remember the equations. So imagine that I take all that time to explain the equation. You don't have to remember it. Okay. So you don't have to remember the equation for this section. However, you must know the basic structure of a triester. Triesters are what we call fats. The layman calls it a fat, right? But we describe them as triesters, right? And how the ester linkage is broken when fats are saponified, right? We looked at that a while ago simply, right? And how in transesterification the alkyl groups of the alcohol right, swaps the alkyl group of the ester. And that's why I looked at the equation. You see how CAPE not make no sense? Because CAPE is going to tell you that you don't need to know the equations, yet you're not going to understand how them swap if you do have the equations. It doesn't make any sense, right? So since CAPE is not intuitive, I don't follow the syllabus directly, all right? So looking at these equations, because we have to use it to understand what's happening. All right, so we have that there. So the ester is more useful as a fuel because it has a lower mass. So notice that though the decannyl ethanoate becomes methyl ethanoate, it becomes smaller. So it moves from 12 carbon to 1 carbon. All right, so the ester is more useful because of a low mass. So a low mass means it has a low viscosity. What does viscosity mean? What does viscosity mean?
Viscosity refers to the resistance of a liquid to flow.
The resistance
It's
of a liquid to flow. Lovely. That is exactly what it is. Some people describe it as the thickness of a liquid. That's not true. So the resistance of a liquid. For example, if you were to pour water out of a jug, right? The water would flow in the normal rate that water flows. But if you were to pour honey out of a jug, the honey would move much, much slower. Honey is more viscous than water because of the resistance to movement, right? It's inertia, right? That's what viscosity is. So because has a lower viscosity, it flows a little bit more easily and it burns easily. So fats and oils can also undergo transesterification, especially in the presence of sodium hydroxide, where hydrolysis also occurs, right? So we have that here. So let's look at this now. We see the movement of the alkyl groups. All right. So I think this will allow you to look at it a little bit better and appreciate it a little bit more. All right. So this is transesterification. This is what's happening. All right. That should be it. So the last thing now is just the key points. So fats and oils are esters of glycerol and long chain carboxylic acid. Look how it's joining. Oh my gosh. Can somebody text in the group and tell Nicholas to join back, please? I accidentally denied entry. All right. Soaps are made by hydrolysis of fats and oils by boiling them with sodium hydroxide, right? And biodiesel is made by the process of transesterification. And transesterification involves the reaction of fats and oils with alcohols of a low relative molecular mass, right? A different ester and glycerol is formed. So notice that in these 4 points, you only get what you need to know and everything else is out. All right? So it's really condensed. So the first thing is just ester nomenclature, ester formation through esterification, right? And then the hydrolysis of esters. And then after that, we went into the formation of fatty acids, saponification, and transesterification. And with that, we have completed objective 2.11 of the syllabus, 2.12 of the syllabus, 2.13. Yeah, so completed 3 objectives. All right. So that is it. So for this evening, what I want you guys to look at now, let me just